Hi and welcome to ACE Teachers Online, a series of online tutorials for students. My name is Joel and today we'll be running through a question from the Preliminary Chemistry Syllabus regarding Hund's rule and order of filling. So this question is really looking at the energy level configuration of a neutral phosphorus atom. And before we can start really answering these questions, there are a few theory concepts we need to run through. These theory concepts include that of quantum numbers, Pauli's exclusion principle, and Hund's rule. Before we can start to answer this question, we really need to look at the main concepts behind it. And the main concepts I've drawn up on the board. So here is our energy level diagram. Before, you might have learnt that the way we write down electron configurations is using SPDF notation. But here is a slightly different way, using a diagram, which involves a few more concepts. Another concept we'll be tackling is the concept of quantum numbers, and we'll go through that in more detail. And that relates back to Pauli's exclusion principle. And before we can start to finally draw up our energy level diagrams, we need to look at Hund's rule. Now, the question relates to our neutral atom of phosphorus. And some things we should know about phosphorus is that we're looking at it in its ground state, so at its least excited state. Phosphorus in its ground state has an atomic number of 15. Because we're looking at 15 protons in a neutral atom, there must be 15 electrons. So when we start to draw up our energy level diagram, we need to really look at 15 electrons that end up on this diagram. Now, how do quantum numbers relate to this? In quantum mechanics, there are 4 quantum numbers that relate to electron properties. And these 4 quantum numbers are that of the principal quantum number, which is denoted by n. That really tells us which shell our electron is in. For example, if n is equal to 1, our electron is in the first shell. If n is equal to 2, our electron is in the second shell, and so on. Our L is our angular momentum quantum number, and that denotes which subshell our electron is in. That relates back to our SPDF notation. So our L number will tell us whether it's in the S, the P, the D, or the F, so on, subshell. Breaking that down even further, we now look at our next quantum number, which is M, which stands for magnetic moment. And what that denotes is the specific orbital within that subshell that our electron lies in. You may remember from your SPDF notation that, for example, our P subshell has 3 different orbitals, px, py, and pz. And our magnetic moment tells us which of those 3 orbitals our electron is in. If we look at S, there is just 1 orbital, and so the electron can only really reside in that 1 orbital. Our last quantum number is that of electron spin, and this quantum number has only 2 properties, either plus a half or minus a half. And sort of, you can think about it as denoting the way in which the electron spins. Plus a half is often referred to as spin up, minus a half is often referred to as spin down. Why is that important when we're drawing up our energy level diagrams? It comes back to Pauli's exclusion principle. Pauli's exclusion principle states that no 2 electrons in the same atom can have all 4 quantum numbers the same. What that then means is that we can only have certain electrons in certain orbitals. If 2 electrons are in the same shell, for example n equals 1, are in the same subshell, for example the s subshell, are in the same orbital, for example, let's look at 1s in this first orbital. They have to have some different property, and then that goes back to electron spin. So if we have 2 electrons in our 1s subshell, they have to have opposite spins, often denoted by that for spin up and that for spin down. So 2 electrons in the same atom can't have the same 4 quantum numbers. So if they're in the same subshell, they need to have opposite spins, is how you can think of it. Our final concept that we need to talk about is Hund's rule. And Hund's rule is a little more complicated. And I'll get to it while we sort of look at our electron configuration of phosphorus. Now, we need to account for 15 different electrons. We've already drawn 2 in the 1s subshell. The next subshell that's going to be filled up is 2s. And again, 2 electrons can fit in our 2s subshell. They have to fit in with opposite spins because of Pauli's exclusion principle. So we've accounted for 4 electrons. Next one that we can fill up is our 2p orbitals. Again, they need to be of opposite spins for those 2 electrons in each orbital. So we'll draw those in. So far we have accounted for 2, 4, 6, 8, 10 electrons, 5 more to go. Next subshell we can fill up with 2 more electrons is our 3s subshell. So we'll put that in there with 2 opposite spins. Now we've accounted for 12 electrons. Our last thing we need to do is account for our last 3 electrons in our neutral phosphorus atom. However, we have 3 potential subshells to fill. Logically, you might think that the easiest way to do this is to put 2 electrons with opposite spin in this first orbital, and then 1 free electron with any spin in the next orbital. However, Hund's rule says that the lowest energy configuration for an atom with equal orbital energies is where the maximum number of unpaired electrons have the same spin orientation. Essentially what that means is first you need to fill every orbital before you can double up on the next orbital. You can think of it as, because we need to have a low energy configuration, 2 electrons in the same orbital are going to repel each other a lot more strongly than electrons in separate orbitals. So we need to fill up separate orbitals first before doubling up. Okay? And Hund's rule also says that these separate electrons in separate orbitals need to have the same spin orientation. So they either need to be all spin up or spin down. So depending on what spin the electron in this orbital is, that will determine the spin for the next electrons. Okay? So we'll draw the first electron in our 3p orbital with a spin up. So then our next electron can't go in there with an opposite spin because of Hund's rule. It needs to go in our next orbital, again with a spin up, also because of Hund's rule. And our last electron will also go in the third 3p orbital. So now we've filled all 3 of the 3p orbitals with the same spin to obey Hund's rule. If our next atom or our next electron was to be added to this, it would go into any one of these with an opposite spin because of Pauli's exclusion principle, which says that no 2 electrons can have the same 4 quantum numbers. So, to answer then our question, we need to look at quantum numbers, we need to look at Pauli's exclusion principle, and we need to look at Hund's rule in order to figure out how to draw in this electron energy level diagram. But your final answer is on the board here. So in answering these questions, we've really learnt a few key concepts that you sort of need in prelim chemistry. And these include, again, quantum numbers, Pauli's exclusion principle, and Hund's rule. And I hope that in learning these concepts, you'll better understand how to approach questions like this.
Thanks for watching this video. For more information, look at our website down below and keep tuned for more ACE Teachers Online.